Controlling characters to perform a large variety of dynamic, fast-paced, and quickly changing movements is a key challenge in character animation. In this research, we present a deep learning framework to interactively synthesize such animations in high quality, both from unstructured motion data and without any manual labeling. We introduce the concept of local motion phases and show our system being able to produce various motion skills such as ball dribbling and professional maneuvers in basketball plays, shooting, catching, avoidance, multiple locomotion modes, as well as different character and object interactions, all generated under a unified framework. Different research has showcased learning basketball plays, but still achieving realistic body and ball movements, high level of detail, and responsive character control from a single model remained unsolved. Our system can satisfy those criteria, and the generated motions appear more fluent and visually appealing. In order to align character movements, a start and end reference pose is usually defined to obtain a global phase parameter. However, using such framework quickly results in mismatching poses when further movements are added. In addition, there can be numerous actions for which it is very difficult or simply unclear how to define a global phase parameter. To overcome such problems, we introduce the concept of local motion phases to align character movements at bone level in an asynchronous manner. For each bone, we first extract the contacts with the environment, followed by a window-based normalization, and apply a frequency low-pass filter to that signal. We can then fit a sinusoidal function which returns the optimized amplitude and phase parameters to compute the motion phase vectors. This technique works in a fully automatic fashion and does not require the animator to define handcrafted rules for each type of motion. We can apply this method identically to very different as well as non-uniform movements in our data. Ultimately, the combination of local phases jointly represents the wide variation of timings for each particular motion. We utilize a deep neural network architecture to learn and control the character motion. Given the user input, our system predicts the character state from one frame into the next in an autoregressive fashion. During preprocessing, we first extract the local motion phases using evolutionary optimization and then feed the complete set of features for the character state and control variables into a mixture of experts model. Here, the gating network dynamically computes the weights of the motion prediction network from the current phase space of the character. We further develop the generative control scheme that enriches the variety of motions that can be generated from high-level user control signals. Our complete network is trained using 3 hours of motion capture data. To train the network, we first extract the locomotion trajectory as well as different action labels from the data. We further compute the contact labels for the ball and end effector joints. We also compute vectors around the character to control various ball interactions and maneuvers. Finally, we extract information about the relative pose and trajectory of an opponent character to learn different player interactions. After training, the user can freely control the character locomotion from slow to fast movements, smooth turning, as well as quick spinning maneuvers. The network can also generate very sharp turns and is robust to quickly changing user control inputs. The character control is responsive and allows the user to immediately speed up or stop moving. Using the generative control scheme, we can further create different dribbling behaviors from randomly sampled noise vectors. By controlling the interaction vectors around the character, the user can create different motions of switching the ball between hands and front or behind the body. We can also create professional dribbling maneuvers by controlling these vectors in a more advanced fashion. The character can also combine such actions while avoiding obstacles on its path. When instructing the character to hold the ball, the network creates a smooth transition and allows the user to freely move the ball around. We can also make the character collect the ball from the ground while running. In order to let the character shoot or catch the ball, we simulate the ball movement via physics when it is not controlled by the character. Our system is then also able to naturally adapt the motion to different physics-generated ball trajectories. The character again can avoid obstacles on its path while running after the ball. The network also responds well to sudden or unexpected changes in the ball movement. We can also make the character perform different movements before shooting the ball into the basket and catching it again. When the player gets close to an opponent that is controlled by another player, both characters will naturally adjust their movements. The attacker can then attempt to steal the ball from the dribbling player. The characters can also create behaviors to block an opponent or to protect the ball from the other player. Also, when holding the ball with a near opponent, the character will try to keep the ball at a safe distance. Comparing the phase function neural network that uses a global phase to align character movements with our system, it shows difficulties learning the asynchronous movements among different parts of the body. This results in stiff movements during various detailed animations. Using an LSTM is another candidate solution for learning such time series data. However, those tend to suffer from strong unresponsiveness or missing detail for dynamic character control. The mode adaptive neural network cannot model back or side walking well as it has no access to the face, although moving straight forward produces plausible results. We now show the learned correlation between the local body phases and movements of the body parts. While deactivating the lower body phases eliminates locomotion but still enables interactions with the ball, the opposite can be observed when deactivating the upper body phases. We can now also apply the same framework to Quattroporte animation, and our network can learn with different modes of locomotion, including pace, trot, and canter in high quality. The local motion phases are automatically extracted from the data, and the network can smoothly transition between modes from the given velocity. We can also make our system learn character scene interactions, like approaching and sitting on chairs, by additionally including a phase for the hip movement. Learning the phase space to pick up an object, carrying it around, and again placing it down at a chosen location is doable as well. In summary, we present a unified framework to learn various context-rich and dynamic character movements, as well as actions and interactions in high quality using local motion phases.